Welcome to my Guide to Computer Forensics and Investigations, 5th edition la- lecture review. I'm not doing labs quite yet. Chapter 7, we're going to be covering Linux and Mac OS. What's really funny is we're focusing primarily on the file system, but a common question I keep getting asked is, why? Why do we have to talk about Mac and Linux if Windows has the majority of the market share? And that's one of the things that our author really doesn't address in depth. When we go to look at a hard drive, if we are looking at being able to capture a disk to image, for example, we're capturing the entire physical disk. It doesn't matter the partition types that are on it. If we're capturing like the logical portion of the drive, then that does matter. But most of my acquisitions have been physical copies to an image, so a whole disk image. So I'm trying to be as less biased as possible. We're going to talk about the Linux and Macintosh file structure. We're going to talk about a few of the Linux tools. So let's go ahead and jump right in. Uh, Big flavors between Linux are going to be the Unix and Linux distros. Linux came after Unix. Unix was the first major flavor. Different types of like Sun Solaris or IBM or AIX, those are common Linux flavors. Not so much common anymore, but I mean, they're still out there. There are some dated systems that use them, but Linux is been slowly taking over that Unix marketplace. Linux has tons of distros. Basically, these are different flavors of Linux, and each flavor, each distro has very common features, but they may have different functionality. How they do certain tasks may be slightly different. Major Linux distros are going to be like Red Hat or Debian or Ubuntu, OpenSUSE, Slackware, CentOS. Those are going to be common Linux distros. Those aren't all of them, they're just, again, the common ones. Again, Linux is the only core of the operating system, the core features, and there are tons of different flavors that do different tasks. All the Unix-like OSs have a traditional kernel, just like Windows has a kernel, and that kernel is the core portion of that operating system. In Linux, the general file structure is going to be just like Windows, where we have certain directories, certain subdirectories that house certain items. And you have to start becoming familiar with the operating system that you're going to be dealing with. I don't deal heavily with Linux in this capacity. I deal with Linux in a different capacity. So the file structure that I learn is slightly different, but it's kind of good to understand where certain things are at. For example, where are logon and log off history information? Well, that's going to be under var, logs, wtemp, wtmp. If you want current login information about a current user, we're looking at var run user temp. If you're looking at uh, account information, that'd be an etc pass wd. Group memberships, etc group. Again, this is not an exhaustive list. This is just common ones that you may have to interact with. Major directories or top level directories: user, etc, home, root, dev, and var. So I'm going to cover these a little bit more in depth just because, again, these are core ones that you should know. USR, user. Most applications and commands are in this directory or its subdirectory. Bins are going to be the binaries, and they contain the files required at boot time. We also have what's called sbin, which requires super user permission to run, because again, bins are just binaries. or libraries that are used by other files to execute. etc, that's where most of the system configurations are stored. Home, that's where all the directories for all users are stored. Typically, it's going to be home, and then they're named after their users. Root, that's the home directory of the root user, that's the super user, and this is kept separate from all the other home directories. Dev, this is where device files, and they'll act as stand-ins for the devices that are present, as described in Chapter 3, like the dev SDA. That's going to be the first non-IDE disk. So all of the hardware objects are going to be in that dev folder. var, this is the subdirectory such as logs. We're going to have a mel subdirectory, which is going to be storing for email. And we're going to have spool, and this is where print jobs are spooled. So there are very specific things in var that we want to pay attention to. So a few things that we have to keep in mind is the Linux/Unix commands, they are sensitive. Capitalization does matter. The book does list a few of the commands, which we're going to be working through, pages 289 through 291. Again, we'll be doing lab videos on the book here shortly. The file structure comes, at least in this regard, we're going to be looking at 3, the extended file system, version 2, 3, and 4. 2 is an earlier one. It was a second iteration of it. Then we got the third, which replaced the second. And the third is the most common in most Linux distros. But because of some hard drive size limitations, we had to get a third variation, or a third iterate of it. And we had to get a fourth iterate. The third took over the second. The fourth took over the third. The fourth version does support larger disk drives. 4 also did things like improve management of the larger files, and it became a lot more flexible with how it stored it. The adoption of 4 is a lot slower in some of the distros. That's why 3 is still the most common. Interesting thing is in 4, everything is a file. Or object. Just like in Windows, everything is an object. So all objects have properties, and there are methods to manipulating those properties. The Unix consists of 4 major components: boot blocks, and a block is a disk allocation unit of at least 512 bytes, contains the bootstrap code. There's only one boot block, and it's located on the main hard disk. Again, as we talked about Windows, notice the 512 bytes. We have a super block, and this will indicate disk geometry, the appropriate available space, and the location of inodes. The super block also manages the file system. Again, if we start relating these back to Windows, segments and tracks and sectors, so they do correspond. So what's an inode? An inode block is the first data after the super block, which is assigned to every file allocation unit. So you'll notice super blocks is disk geometry and space, kind of like the indexing. MBRs, GPTs, things like that. Then inode blocks are where the file allocation is actually taking place, the storage of the files. Or at least it's going to be the beginning of each of the files. Notice it says file allocation unit, not actual file allocation, because our last major block is a data block, and this is where the directories and the files are actually stored. So there is a very specific data block. Notice that a data block is linked directly to those inodes, because inodes point out the beginning of those files and folders. Inodes contain files and directory metadata. They also link the data stored in the data blocks. They are assigned inodes containing the following major information. An assigned inode, mode and type of the file or directory, the number of links to a file or directory, just in case the data is fragmented, the number of links, we already talked about that one, the unique identifier and the global identifier of the file and or directory's owner data, directory information, whether it be a group or a user, the number of bytes in the file or directory. Lastly, the file or directory's last access time and last modify time. Inodes are also last file status change, the block address for the file data, indirect, double indirect, triple indirect block addresses, just again, if it's fragmented, the current usage status of that inode, the number of actual blocks assigned to a file, again, if it's fragmented and it has to span over a wider area, or how much of a portion of a disk does that file need. Those are done in blocks. Notice here we're talking about blocks instead of segments or clusters. File generation numbers of a version number. The continuation of an inode's link, because again the inodes link all of the data blocks together. So this is where it gets really interesting. The first inode has 13 pointers. Pointers 1 through 10 are direct pointers to a data storage block. Pointers 11 is an indirect pointer. It will link to 128 pointer inodes, and each pointer will link back directly to 128 blocks. Pointer 2 is a double indirect. Pointer 3 is a triple indirect. So what are these pointers? This is just about the way that we're doing our linkage between blocks. Again, block is going to be the smallest measurement that we're using here. We call them segments on a Windows hard disk, but this is pretty similar. We have bad block inodes as well. This keeps track of the bad sectors. In Windows, we call them bad sectors. In Linux, we call them bad block inodes. So to find the bad blocks, we can always use some type of file scan or bad block scan, or make a MKE2 file scan, or some other type of safeguard that basically writes that those are bad blocks and we stop using them. The hard links, these are pointers that allow access. It allows accessing the same file by a different file name. We can use the ln command to create a hard link, because sometimes there may be portions of a file that is identical to other files. So instead of having to create 3 different files, we can create a hard link so that we have just one set of data that all 3 of those files reference. We have a link count, and these are field inside each inode that specifies the number of hard links. We also have navigation dots, dot versus dot dot. A dot will indicate the current directory. A dot dot indicates the parent directory. If you ever do like a CD dot, you can actually navigate to your current directory. If you do CD dot dot, it moves you up one directory. But that's more for our Linux course, which those videos will be coming shortly. We also have what's called a symbolic link. These are pointers to other files that aren't included in the link. These are also called soft links or symlinks. They are point to other drives or other parts of a network share that aren't on your physical system. Having an inode of their own is not the same as an inode of the item that they are pointing to. Keep that in mind. So depending on the existence of the destination, they're going to be maybe pointing to. Here is a example of a hard link and system link. Here you actually see the symbolic link with the hyphen and a caret, or sorry, hyphen and a greater than sign. Honestly, you see the same thing in Windows. We have symbolic links, we have junction links, we have hard links. We have the same thing in Windows. All right, moving on is our Mac structure. So this came from our author, so keep in mind that things like Mac OS X versions, Maverick, and Yosemite, which we're talking about being released, are kind of dated. We're past this now. Currently, we are using Mac Sierra, which was released September 2016. Sorry, released September 20th, 2016. So Yosemite is kind of dated. OS X is built off the core called Darwin, and Darwin is basically it's a combination of BSD, which happens to be one of the earlier Unix. Mac OS X has moved to the Intel processor, and it's become Unix based. Honestly, if you look at a Mac's hardware, it's the same hardware as a Windows PC. The difference is the software. A Mac hard drive is a traditional SATA drive that you'd find in any Windows PC, current Windows PC. Processor is an Intel-based processor. Video cards are the same common video card that you find in Windows PCs. So again, hardware-wise, Mac and PC are damn near identical. Software-wise, they are not. With that said, Mac has two common file structures: the hierarchy file system and the extended format file system. HFS and I cannot talk today. HFS Plus. These are introduced in an earlier version of Mac OS X. Sorry, Mac OS 8. Mac OS X is Mac OS 10. And they do support smaller files on larger volumes. Basically, this results in more efficient disk usage. So if we're looking at the smallest block, if they're able to be a little bit smaller and you don't fill them up, we don't have a lot of wasted space or slack space. In a Mac, a file consists of two parts: a data fork and a resource fork. The source file metadata and application information is also stored there. The data fork typically contains the data the user creates. That's going to be the application that also will read and write to that data portion. A volume is any storage medium used to store a file. Not quite sure why we had to throw that in there. So if you look at a file, the resource fork is going to be the resource map and all the resources used for it, and the data fork will be just the data. Our volumes will have an allocation and logical block. You'll notice the logical blocks don't exceed 512 bytes. Not saying that they are 512 bytes, but they don't exceed it. So the allocation blocks are a set of consecutive logical blocks, and two of the files will have an EOF, end of file descriptors. We have a logical, which is the actual size of the file, and we have a physical, which is the number of allocation blocks for that file. So let's look for an example. Here we have our file allocation. We have the appropriate logical blocks for the appropriate files and allocation blocks. If we look at file B, again, here we have the logical blocks. Again, notice the 512 byte cutoffs. All right, so moving past that, we have what's called a clump or clumps, and these are groups of contiguous allocation blocks. This helps to reduce fragmentation. Older Mac OSs will use the first two logical blocks, 0 and 1, as a boot block. That's going to be containing our master directory block, MDB, or our volume information block, VIB, and this is going to store the information about the volume. Then we have a volume control block, VCB, which will store the information from the MDBs when the OS is mounted. Again, pretty similar to Windows, except we're just changing the names. We have a master boot record, which is very similar to the master directory block. I know they're not 100% the same, but I mean, for this level of understanding, they're going to be damn similar. We also have what's called an extended flow file, and this is going to store any information not in the MDB or VCB. We have a catalog, and this will list all of the files and directories on the volume, pretty similar to like an index. That will maintain the relationship between files and directories. We have a B tree, and this is the file system in earlier Mac versions, and actually the actual files data that is stored is going to be a leaf node. It will use a header and an index and a map node to map it. But again, that's for older versions. There are some differences between Mac and Linux, of course. Linux has home/user and root directories, where Mac has the users/users, username, sorry, and we have a private var root file. So instead of Linux having home/username, Mac has user/username. Again, very similar to Windows, not 100% identical, but damn similar. That home directory does exist in a Mac, but in a Mac, this is empty. Mac users have limited access to other users' accounts, so files and guest accounts are disabled. Mac users have limited access to other users' accounts, files, thus, the guest account is typically disabled. For forensics purposes, Mac OS X, you must know what the file system components are, where they're located, how both the files and components are stored, how the application settings are stored and how they're formatted, plain text, a plist, and the SQLite database. Those plist files are preferred files for installed applications. We also have what's called a file vault, which is used to encrypt and decrypt users' directory. We have keychains, and these are files used to manage passwords for applications. The Mac application keychain access actually is what manages them and allows you to enable and to restore passwords. Deleted files go to the trash folder. If a file is deleted with the command line, here it doesn't show up in the trash folder. So that's kind of interesting. Slightly different from Windows. Acquisition methods for Mac make an image of the drive, the entire disk. Static acquisition of the suspect drive is preferred to that live acquisition. So power it off, full acquisition using a write blocker. Removing the drive from the Mac Mini CPU is very difficult typically. So this is one that's going to require some practice. Attempting to do so without Apple Factory training, you can damage it. We are going to be looking at Apple training coming up. Not quite sure when I'm going to get to those videos, but I am looking at doing a full section for Apple training. Uses a Macintosh compatible forensics boot disk, especially if you're leaving the drive in the Apple computer. You're going to want a Mac or Apple boot disk that will allow us to use the tools. The acquisition methods, we also have what's called black bag technologies. That actually is one tool that does sell for macOS. Some other tools like Macquisition. Again, these are fairly old. There are other tools out there that will do it, but you gotta go back to what is your organization using and is there a procedure for it. Part of that black bag uh, does have full forensics tools and can disable and enable disk arbitration. It does begin to turn off and mount functions of the OS X, so it will allow you to connect a suspect's drive to a Mac without a write blocker device. But again, with this, it goes back to follow your organizational policies if you need a write blocker or not, just in case. Other tools that are out there, guidance, X-Way, access data, those are all tools that should be able to access it, but again, verify and check. Common commercial tools, there's a lot of freeware tools, but again, pay attention to what tools your organization is allowed to use. For Linux, we have what's called Autopsy. We're going to do a few of those labs in class. Not quite sure why we're going to talk about tarballs, but we are. A tarball is a data file containing one or more files. This is very similar to a zipped file. Uh, Here is one forensics tool. This is the start of Autopsy. Here's another Autopsy window. You can examine a case using these tools. We do have steps in our physical book, which we're doing separate videos for those. And they're very big with showing you screenshot by screenshot. All right, that's the end of this lecture. Again, understand the main differences between Windows, Linux, and Mac when it comes to file structure. Make sure you understand the extended file systems version 2, 3, and 4 for Linux, and understand the HFS for Mac, and kind of how they relate back to Windows. That way, if you understand that, you can understand things like the boot blocks, the super blocks, the inode blocks, and the data blocks, and the data forks and resource forks. It makes it easier to reference them back to something that you understand. We talked about the HFS, the HFS Plus, and again, pay attention to the Linux forensics tools. Some of them are free, but you have to make sure that your organization is allowed to use them. If you have any questions, please let me know. Thank you.